Of course, we are not going to look for each data because these are data from the handbooks. However, just one comment. Of course, so each data has to be looked for in a book, but there are two particular cases. It is the manganese and it is the iron. In case of the iron, you have at least two. You have FeO and Fe2O3. Okay, this we don't need. You probably know, in case of iron, we have Fe, we have FeO, we have Fe3O4, and we have Fe2O3. And the ores are mostly this one, the so-called hematite ore. But you may have this one. These are the so-called magnetite ore. But actually, the magnetite is not, in reality, it is just the combination of FeO, Fe2O3. You see, it's the combination of these two gives this. You see this? This is a particular feature. And then the iron, since it is the largest in quantity, it has been very nice to the metallurgists, because when you look at the reduction heat, when you go from this to this, from this to this, from this to this, for each step, the reduction heat per kilo oxygen is the same. And therefore, you see, for the iron, I've put only one value. Per kilo metal, it's 1.3. Per kilo oxygen, it's 4.59, 4.6. But it's the same at any step of the reduction. So, with the only thing that matters is the amount of oxygen over iron. And you see, in Fe2O3, the O over Fe is 1.5. Huh? In FeO, the O over Fe is 1. And here in the ore, in this ore, we have only Fe2O3. So O over Fe is 1.5. So for iron, things are simple. For manganese, things are not simple, because when starting from MnO2 to MnO, the value, the reduction heat per kilo manganese is 2.6, and for the step from MnO to Mn, it is only 1.95, and so this has to be considered, of course, in the balance. Okay. And now one last comment. You can see that the values here are variable, of course. They are higher for the metals having more affinity with oxygen, of course. But what is very significant is that you see, I don't have it for aluminium, but I can tell you the result for aluminium, which is above, which is here, aluminium, above SE. The result is 8 point something. So in a family, the figures per kilo oxygen are comparable. And you see, again, for chromium and manganese, of course, here the values are a bit different, but if you take the medium between these two, it's about the same like this. Because this is for Mn, it is two values from MnO2 to MnO and from MnO to Mn. If you take the medium value, it's about the same like for chromium. And below this, the family of the metals which have low affinity, it's again, you see, the value, the figures per kilo oxygen removed is about not constant, but it's very close. While the value per kilo metal is variable, but per kilo oxygen it's close to one figure. I think it was worthwhile to translate the handbook values into this value. This gives you an insight of the importance of any metal in your analysis. So it gives you a view of what is more important and what is less important. Okay, let's go to the calculation. These are the so-called thermodynamic data. Now we need other data before doing the calculation. We need this data. These are the data for calculating sensible heat. And also, here I have taken data from handbooks and I have translated it in the system kilowatt hour per kilo. Now, you see, 1 kilo slag at 1400 degrees C is including 0.51 kilowatt hour per kilo. 1 kilo metal at same temperature is including 0.4 kilowatt hour per kilo. And if the temperature is different, the calorific value enables to calculate. Meaning, let's take an example. Metal 1400 degrees. The enthalpy, meaning the sensible heat content, is 0.4 kilowatt hour per kilo. Now the question is, what is it at 1300 degrees? Just before all, to give you an idea. The enthalpy of the solid is like this. And then, when becoming liquid, makes this, and then it's exaggerated. It's like this, huh? Liquid. And the method we're using now is that if that is the value at 1400, we want to know the value at 1300, no, 1300, provided it is still liquid. You see what we give. This one is this point. For 1400 degrees. And to calculate this, okay, we give not 10 figures, 10 values. We give this, and we give the slope. The slope here. This is the CP, meaning that the exact value I want to calculate is this, but using the slope I calculate this, which is a bit different, but I have exaggerated the difference to explain. So, and the calculation is H minus the slope you remember the enthalpy or the sensible heat is in general mCp times T. But this is not correct in absolute, because you see when changing the physical form, when going through the liquid, it's not simple like that. But this is this is H. Excuse me. But inside a domain of liquid, for instance, it's correct. And what you can do, it's use it in delta H times delta T. So, do you understand? So this is exactly, so we have, you see, we have the value at 1400 degrees, we have the value, and we have the CP for each, for the slag and for the metal.
But this depends on the composition of...
Yes, you are right. And that's a bit a problem. Because you will not find a book for CP and H for any composition. So what you find is a book for slag of blast furnace, a book for maybe for one slag of ferromanganese. I got it from ferromanganese blast furnace, because in France until a few years we had blast furnaces, and okay, I I have made some calculations.
But you must have some database regarding the, no?
No, you will see in the handbook you find. You have, what you have is some data for FU. You have some data for MNO. You have some data for SCO2. But it's not correct to say you make the sum times percentage. It's not correct. You cannot do this. The simple reason is that at 1400 degrees, this is liquid, but this is solid, I think, and this for sure is solid, and MgO for sure is solid. So you cannot mix things that are liquid and solid. So the only way is you must use data that you find, that some researchers have measured in the laboratory. And okay, you have these data may not be the best data, and I ask you if your researcher at Guangyan have let them check, because I have it from the ferromanganese blast furnace, but it was a blast furnace working with poor slag. So it is not the same slag, exactly. But it is the best I have. That's live. Okay? For the gas.
전체 그 물레별로 다 해야 된다는 얘기네 그러면.
아니요, 원래별로 해도 상이 다 다르기 때문에 제가 할 거는 계산이 안 맞다는 얘기죠. 이 사람은
그러니까 저거는
실험 결과.
그러니까 저게 따로 원래별로
네.
우리가 같은 게 쓰는 원래별로 뭐가 우리 다 있어야 된다는 얘기잖아. 있다가.
그렇죠. 저런 식으로 배합이 된 것들이 샘플 애들이 다 있어야 된다는 얘기죠. 계산해서 나오는 게 아니라는 얘기죠. 저렇게 할 수 없다 그러니까.
저게 골치지 저러면 계산이 결국 안 되는 꼴이지 뭐.
You don't agree?
No, it's very serious force. Then we cannot calculate the energy balance without any the reference data.
These data are not false. They are not very accurate. But okay, you know, the balance is not a balance at accurate at 0.1%. It's not possible. It's just not possible. Because it's enough to do it with some inaccurate. Of course, you cannot have very inaccurate data, but on site the charging weight is measured with an accuracy of how much?
Yeah.
At least 1%, because it's by the analysis is measured with an accuracy of few percent. You have seen. So it makes no sense to target 0.1% accuracy in the balance if what you measure is inaccurate by 5 or 10%.
If we change the ferroalloy raw material, then we have to change.
Yes.
And so
yes.
we have to know chrome, silicon, manganese,
Yes.
aluminum,
Yes. Yes.
calcium.
You have you will see for ferronickel. I did not change it because I did not find it. I have to look for better data. These are data which are correct for I think for ferromanganese, but I think they are correct for ferromanganese, but for slag, I don't know the difference between poor slag and rich slag, which has more or less MNO. I don't know the difference. Of course, it makes sense to look for the best figures. but you must find it.
Will you prepare the material thermal data for nickel, mangan, silicon, chrome, aluminum for us? It's the data.
I will try to find something, but I kindly ask you if you can ask your researchers what they have.
You have experience, and so we receive the reference, and then after that we can check it. But we we have no knowledge for that, and we cannot approach it. So if you give the data for each ferroalloy, and we can start through our research members.
좀 애매하네요.
이건 뭐 어차피 그렇게 된 맞춰서 또 찾아보자고 좀 더. 일단
Okay.
아는 게 중요한 거 지금은.
So for sure, ferromangan,
silicon,
ferronickel,
nickel,
ferrosilicon,
How about chrome and aluminum? Is different?
ferrochrome.
Aluminum is fully
No,
different.
but yes, but aluminium is not
Not
produced in SAF.
Not.
Aluminium is electrolysis. But ferrochrome, I can think. Okay. For the gas, it's the same, but for the gas, of course, we know exact values. But for the gas, again, for the gas, for CO2, of course, we have the values. I think for CO and CO2 is the same sensible heat, and the result is that actually we use only this one value, and if the temperature changes, the assumption made is that it is linear. In reality, it's not fully linear, but it is assumed to be linear. Okay? Okay, these are the thermal data, and then again, for doing the energy balance, we have to set a charging rate, and here I have set the charging rate to obtain 10 tons ferromanganese per hour, because this is roughly the figure of high metal. And it's a good example anyway. And 10 tons of ferromanganese per hour requires, you see, this is just obtained, the ore is just obtained dividing by the amount, by this value, which is the metal yield of the mass balance. And actually, I should. What is not good here is the input is not that one. This should have no color, and the input, the value input is this one. This is what is input data. Then we have to indicate the material preheat temperature. I explained this. This is the temperature of the material charged. And in case of ferronickel, it will not be 0 degree. Here we take 0 degree. We have to give a temperature of the process gas. This again is a kind of is a guess. We can calculate it better, but it is not so important. But it is anyway. It is a temperature. It cannot be 100 or 200 degree, and it is not 1300 degree. So it is a temperature in between, and this can be estimated more accurately doing the partial balance. So if you want, we can proceed to that. But okay, afterwards we will see the influence of each parameter, and you will see this is not a measure parameter. This is 700 degree. Of course, for the material preheat temperature, this can be a measure parameter, because the choice is between 0 and 700. That's a big difference. But here, for the process gas temperature, the choice or the error is between 700 and 600, or 700 and 800, so the error is not so large. Okay. Okay. I think that's all all data for making the calculation. So we begin. Maybe we begin with the process gas, because you also asked me how is this calculated. The process gas amount is in cubic meter per hour. Is just saying it is per ton of ore. There is a factor of 10, because here all is calculated per 100 kilo. Then you multiply by the amount of carbon, of reducing carbon, that is the carbon which is transformed in CO2, and you multiply this by this value is the ore charging rate, is the 24.8 ton an hour, and then you multiply by 22.4 over 12. This is the discussion of yesterday with when transforming carbon to CO. 1 mole carbon is 12 gram or kilo, and this gives 1 mole of CO, which is in kilo. Of course, in kilo it is 28 kilo, but in mole it is 1 mole, and 1 mole gas is always 22.4 cubic meter normal. So the amount of gas is the kilo of carbon. This is the kilo of carbon times 22.4 over 12. Everybody agree? Okay, so this is the amount, and here this is two things. This is the heat content of the process gas, that is of the CO and CO2 leaving. It has two parts, this term and this term. This term, the first one, is the chemical heat. And the chemical heat is the heat content, the calorific heat when burning the CO. And this, look, we take here again, this is 10 times the kilo of carbon times this is the charging rate. Okay?
What's the process chemical thing and plus?
This is, there are two terms. The first one is chemical heat, and the second term is sensible heat.
Sensible.
Yeah. And you see the first is the kilo of carbon, the total kilo of carbon, the same number we have seen before, but multiplied by, look, by 1 minus PCR. Why? Because this gives you the amount of CO. Look, if you forget this, this is just the same than before. It's the amount of gas produced. The formula, the first term is the same formula than for the amount of gas, except that you multiply by 1 minus PCR to only select the CO, because CO2 has no calorific value. Shall I detail it more?
Yes.
It is air 34 is kilocarbon per 100 kilo or, and then this I multiply by air 53 by or rate in ton per hour, and I have to multiply it by 10 because this is for 100 kilo, and I give the ore rate. So this is the kilocarbon per 100 kilo, this is the ore rate, and this times 22.4 over 12 until here I have nothing other than the volume of gas, of CO plus CO2. And now I want to just know the CO. I multiply by 1 minus PCR. And this is, in our case, it is 0.80. Because PCR is CO2 over CO2 plus CO2. So 1 minus PCR is CO, or CO plus CO2. And that is what I want to know, the amount of CO inside the volume of gas.
글자는 제가 뭐라 쓴 거 CO 플러스 CO2 볼륨 오브 뭐냐? 볼륨 오브 가스는
Can you let me know the letter? The
Volume
volume
of gas.
volume of gas.
Volume of gas
Yes.
in normal cubic meter per hour. And then here is the volume of CO. Okay? And then this volume of CO I multiply by T50, and this is the calorific value of CO gas is 3.5 kilowatt hour per cubic meter.
No.
Okay?
(22.4가) 않고
부피.
빈가? 볼륨으로 계산한 거구만.
Sorry, we're not finished, of course. This was the first term. The first term, and the second term is the sensible heat. So, for this, it's a bit different because you see for the gas sensible heat, the data, the thermal data is given per kilo. So I cannot use the same because this is a volume times a calorific value per volume. And now I want to calculate the sensible heat with a calorific value per kilo. So I have to recalculate the gas rate, but in kilo. And so to do this, the simplest way is that I just say I don't recalculate the CO and the CO2 separately. I say that the CO plus CO2 is just the sum of the oxygen and of the carbon, disregarding the proportion of CO and CO2. For sure, the CO plus CO2 weight is the weight of the oxygen input and of the carbon input. You agree? These are these two. And then I multiply again by the rate, the ore rate, the 24.8 ton an hour, and then I'll multiply by the CP. No, excuse me. Not the enthalpy. By this, by the enthalpy. By the enthalpy, and this is, if it is at 8, until now, it's the enthalpy at 800 degrees. And if in reality it is different, I'll multiply it by the temperature, which is the input temperature, the 700, divided by 800, using this assumption of a linear behavior of the enthalpy. Maybe I develop this also to be sure. Huh? So this is chemical heat of gas. And now I write sensible heat. Again, I say it's 10 times kilo CO plus CO2, and this I say it's the same than kilo C plus kilo O. And this is per 100 kilo. This. So times 10 and times or rate in ton per hour times enthalpy at 800 degrees times temperature, the real temperature, and in this case it's 700, divided by 800. Okay. Okay.
지금 메저링가는 그래프 범법수가 한다는 정도만 실제로 딱 머릿속에 이해는 안 됐지. 그래서 일단 보고 내일 하루를 비우고 내일 하루엔 다른 얘기를 하고 공사가 그 관련된 거를 좀 하루 정도 민가장에 뜯어보고 질문을 그 다음에 질문하면서 다른 그런 느낄 거를 해보는 방법을 좀 택해야 되겠다는 보니까 그지? 일단 한번 들어보자고 이제.
Why T divided 800? Is it delta T?
No. In case of gas, you see, in case of liquid, it is a delta T. I use a delta T in comparison with a reference temperature which is 1400 degrees C.
No.
Here.
That is not gas.
left side.
Yes, and yes, but here it's not a delta T, but it's just a T, because this is,
Basically, the up
this is
gas
zero.
temperature,
Yeah.
up gas temperature difference is 800 or 700, isn't it?
Yes, but what I say is that the enthalpy at 700 is just the proportion of the temperature.
Yeah.
It's I make no I have no CP. I could use the CP also, like for the other data. This is possible, but you know, we will see that this is not so dramatic. It's not so important. You see, for all these data, I use CP to calculate a variation.
Yeah.
In this case, I don't need to use CP because I don't. There is no change of physical properties.
Yeah.
It's always gas,
Yeah.
and this is not so. Okay, it's not well drawn, but it's practically linear. Therefore, the enthalpy is proportional to the temperature.
800보다 700 해가지고
결국에 그만큼 수정한 거예요.
그만큼 내린다. 그러니 약한 감도 그렇지. 락하게 주죠.
저렇게 풀어야 되나?
And in this case, it is not the case. Huh? Here it's very different because it's not linear, all this stuff. It's only linear in a small area. But here, it's the same gas, it's no change, so it's practically linear.
Normally, we know very well the CP or enthalpy of the gas,
Yeah.
right? And we can use that one directly.
If you want to improve this, it's no problem. Let me just show you the importance. Here the result is 5,622 when using 700. If I use 800, it's 5,819. So it's 270 difference over a total of 52,000. So it's 0.5, or how much is it?
Okay, I see. Just
It's very small.
just
And if you improve you can you can improve it. It's not difficult.
at the beginning anyway. You got the data from 800 degrees Celsius from
Yes.
gas, right? But you want to convert to 700.
Yes,
That's
exactly.
why you use it like
Yes,
that.
yes, yes.
Okay.
Yes. The data for 800 is correct, I'm sure. And what I just say, I don't, because, you know, for the gases, the data are well known. You can use a table giving you the enthalpy at 0, at 100, at 200, etc. But if you want to do this, you can do it. It's possible. But I simplify it because I just assume that it is linear. In reality, it's not completely linear.
Okay.
But the biggest uncertainty is the choice of this temperature. Is it 700 or 800 or 600? But showing you this difference, small difference, it shows you that it makes no sense to spend one day about thinking, is it 800 or 600? This is not making the difference in your in your balance. You will see other points that are much more important. And now, let's put 700 again. And now, let's change. What can we change? The PCR, which will change the calorific value, because it changes the CO. So we put 0.7. This is more complex now. It's not correct. You see, this is a big change.
Yeah.
But
Yeah.
what you did not see is that this is change also. Because if you change the PCR, you change the carbon consumption.
Yeah, of course.
You understand?
Yeah.
So it's not so easy to say. And so what we should check is the difference, actually the difference between these two. So, of course, PCR has to be, you must think over PCR. But the base of thinking over PCR are the physical, the physical and chemical situation of height of layer and reducibility of the incoming ore, of the first oxide.
지금 PCR 바꾸면은 C 들어가는 비율도 다 틀려지거든요. 그러니까
바꾸면 직접 바꾸면 말이야.
방금 그거 CO 비율 바꿨죠.
PCR 바뀌잖아.
CO 바꾸면 PCR도
그렇지, 그 바뀌지. 그 얘기가
바뀌니까 C량도 다 달라지는 이거 바꿔갖고는 그거 바꿔갖고 이 가스량이 2배나 차이 나면은 제법 많이 바뀌는 거거든요.
좀 많이 해가지고 많이 바뀌는데 그렇게 바뀌는
이거 지금 뭐라고 얘기해야 될지 모르겠네.
I'll just check. It's interesting. It's not a big influence as well. I was thinking. Let me show you. PCR. Now we have 0.6 and 0.8 PCR. Or C over 0.6 PCR 0.8. And look, what is important is the two terms that are changing are this one and this one. But the important point is how does the difference change? Meaning that if this increases and this increases also, it makes it's the same. You understand? For the balance.
I know that, but the carbon input.
Yeah.
Carbon input amount is different. Can be changed.
Exactly.
Yeah.
But what I say is that for the result of the balance, for the calculation of the electricity, what is important?
There is the same.
What is important is the difference between these two. You understand? Because this is the total carbon input energy, and this is the lost carbon energy. Understand what I mean? So, the total carbon energy input is 25,400. The carbon energy lost, because this is the part of the carbon energy which is not used. It is going out in form of sensible heat of gas and of calorific value of CO. So the difference of these two is the efficient, is the carbon energy used efficiently. You agree? And what I want to show you is that if you change the PCR, the difference is not so much changed. Look, here the difference is 25,400 and 5,600. Roughly, the difference 20,000. Agree? Okay. Now we change PCR, or we change C over O. We put 0.7. So the resulting PCR is 0.6. It's a good change of PCR. And look, instead of having here 25,000, I have 29, nearly 30,000. But here I have, instead of having 5,000, I have 10,000. So the difference is about the same. Meaning I put more carbon energy in, but I lose more energy of carbon just because I have more CO gas. Because PCR is worse. But the result here is about the same. The result of electricity needed is not so much. It's a bit higher. It's a bit higher. Of course, it must be a bit higher because. But you see, it's a marked change. It's a notable change of PCR. But the influence is not that big. It is about 1,000 more here. 1,000 more.
아, 백회사가 2배 커져도 그만큼 카본을 더 넣어버리니까 카본 에너지를 더 넣으니까
27.5.
중요하지 말고.
The result here is 27.5 megawatt. And if I go back, just go back like this. Yes. It is 26.7. So it is less than 1 megawatt change. Okay? No, let's move to the reactions. This is a complex formula, but actually the principle is very simple. The principle is that, again, you take the factor 10, because here all is given 400 kilo. The factor 10 is to come to 1 ton. And what is done is simply that here you have the amount of oxygen which is really removed. Here you have the oxygen and you multiply by the yield of reduction to have the real oxygen removed, and then you multiply by the reaction heat per kilo oxygen. And this you do for each line which is used. Okay, normally here you never reduce, and you never reduce calcium, etc. vanadium, and you do it for each line. And the addition of all that gives you the reaction heat, meaning the reduction heat, the total heat for the reactions, while on the opposite, the heat of the carbon oxidation is given in the input time. And here you have all these reduction heats plus 1 turn The last is one specific term, this one. This is the term of evaporating the moisture. But this is very small, but anyway, the average moisture is this, and so we say the amount of vapor, the amount of water vaporized is the amount of ore times the moisture times the factor 0.7. 0.7 it's again an approximate value. Vaporizing water requires 0.7 kilowatt-hour per kilo. Here again, if you want, you can insert better formula, but normally the moisture heat is small against everything. But it's better to use it than to do nothing. You understand the principle of this formula? All other factors before is just multiplying the kilo oxygen by the reduction yield, which gives the real kilo oxygen removed, and you multiply by the heat and by the column giving this heat per kilo oxygen. So this is the reaction heat. Shall I explain for one example, for one line? Or?
Yeah.
Okay, let's do it for the first one, for silicon. Silicon, I take, this is 12. So, it's Q12, this value 4.3 kilo oxygen per 100 kilo, or, and here before we have the factor 10. Of course the factor 10 is for all the same. We take this 4.3 kilo oxygen per 100 kilo ore, we multiply by 2% of this 4.3 will be only removed, because silica is practically not reduced, only very few. Multiplied by 2% by R12 over 100, and you multiply by U12, which is the heat of reduction per kilo oxygen. And the rest is always the same for all others. Okay? Except this additional term of water vaporizing. I have put here, should not forget, but
Add the reduction heat for water vaporizing.
No, it's not a reduction heat. This is another reaction,
Yeah.
a separate reaction.
Not reduction.
It's the water that is that evaporized. The water doesn't even slag, metal. When the gas CO coming out, this is ore, and this is heated, and when here you have 1400, and I don't know exactly how is the temperature distribution, but as the temperature reaches 100 degrees, the water vapor will escape. Of course, in theory, we should add this to the gas volume, but it's very few. It's very few. Just to take account in the calculation of the energy requirement. Okay. And now, for the sensible heat, it is rather simple. It is the sensible heat of the slag and the sensible heat of the metal. And it is just saying that I'm just wondering. Yes. Okay. This is, you see, this is the amount of slag per 100 kilo times 10. This is the amount. No, sorry. This is the amount of metal times 10. This is the amount of slag times 10. And this is
위에 계산 100kg를 내고 일단 톤을
and this one is these are the thermodynamic data. This is the H for 1400 degrees, and plus the CP times the delta T. This is what it is exactly this one. And the same for the slag. Yes, it is here. You see, this is the enthalpy of metal at 1400 degrees, and if the temperature is different from 1400 degrees, we add a variation, a delta H, in which we use this CP, that is the CP, times the temperature difference, the difference between the real temperature and 1400 degrees. In our example, we have 1400 degrees, but if there is a difference, we calculate it. And exactly the same for the slag.
그러니까 내가 거의 이해가 안 되는 것들이 좀 많이 있는 것 같은데 저도 이해가 잘 안 되고 진짜 좀 계산 어렵게 엑셀 만들었는데 더 쉽게 만들 수 있을 것 같은데
오케이.
이해하면 쉽게 만들 수 있을 것 같은데.
이해 안 해도 쉽게 만들 수 있을 것 같아.
Of course, you see that in case of ferromanganese, that's not the same for ferronickel. The biggest term is the reaction, and therefore it's important. Indeed, it's important to have the good. You see, for ferromanganese part, the most important input data, literature data, are these heats of reduction. Because if I have a false figure here, of course this term, the reaction term, will be strongly different. But of course the sensibility is important as well. And you're right saying that when changing the type of ferroalloy, it's better to find exactly adapted values.
일단 보고 안 되면 이해가 좀 덜 되는 부분들은 내가 생각할 때 지금 오늘 일찍 마치고 오늘 하고 내일 오전이나